Hi everyone, and welcome to the video that is on the basic concepts of chemical bonding. And this is based on 8.1 to 8.3 in your book, and we're just going to focus on the different types of bonding. So there are three basic types of bonds. First we have ionic. Okay, ionic bonds are based on the electrostatic attraction between the ions, and this is really based on the transfer of electrons. Then we have covalent bonding. And covalent bonding is based on sharing of electrons. And then third, we have metallic bonding. So metallic bonding is when you have metal atoms bonded to several other metal atoms. And this is based on delocalized electrons, or the sea of electrons you might remember from last year. So we can have ionic bonding, covalent bonding, or metallic bonding. So before we even jump into the types of bonding, I just want to briefly look at Lewis symbols. So G.N. Lewis developed a method to essentially talk about the possibility of forming chemical bonds. And what he did is he used one dot for every valence electron. So if you take a look at this table 8.1, notice that lithium has one valence electron. It has one dot. Beryllium has two valence, has two dots. Notice carbon has four valence electrons. Going along with Hund's rule and with orbital diagrams, if there are four valence electrons, we want to place them one on each side before pairing them up. Now it doesn't matter where you start. You can start wherever, work your way around, but just make sure you have one valence electron on each side before you pair them up. And when forming compounds, G.N. Lewis talked about how atoms tend to gain electrons, lose electrons, or share electrons until they have 8 valence electrons. And this is essentially the octet rule. So to start, we're going to focus on ionic bonding. Now, if you want to watch a catchy song about bonding, ionic covalent, you can actually go to this link, which I will also post this link on the class webpage. It's just another chemistry teacher who made a really catchy song that you might find interesting. So we're just going to look at binary ionic compounds. So all that means is we have a metal plus a nonmetal, and it forms a salt. So we have a solid metal, we have a gaseous nonmetal, and it forms a solid salt. So ionic compounds are all about the electrostatic attraction between the positive metal cation and the negative nonmetal anion. So what happens is our metal gives the electron to the nonmetal. The metal becomes positive, the nonmetal becomes negative. So with ionic formation, like I said, atoms tend to lose or gain electrons to make them isoelectronic to the noble gases. So just remember, your metals lose the electron, your nonmetals gain the electron, and that corresponds to ionization energy and electron affinity like we talked about in Chapter 7. So as we saw in Chapter 7, it takes energy to remove electrons from a metal. So ionization energy is the energy required to remove an electron. This takes energy. This is endothermic. But when we form an anion, typically, that's the electron affinity, typically that's exothermic, right? The energy is negative, that's exothermic. So we actually get energy back by creating the anion. But these numbers don't explain why the reaction of sodium and chlorine is so exothermic. And you can actually watch this video on the class website as well, and just take a look at how exothermic the reaction is. You kind of get a little idea in this picture. But it's a very exothermic reaction. So ionization energy and electron affinity alone don't explain this reaction. So what there has to be a third piece to the puzzle here. And what we haven't accounted for is that electrostatic attraction between your positive cation and your negative anion. So this just summarizes each of those slides. We have ionization energy that is endothermic. Electron affinity is typically exothermic, but the formation of the solid is very exothermic, and we have to figure out why. So this third piece of the puzzle has to do with lattice energy. So lattice energy is the energy required to completely separate 1 mole of a solid ionic compound. Essentially, lattice energy is the energy required to break a bond in an ionic compound. It's the energy required to break that ionic bond. lattice energy is associated with Coulomb's law. So we've already discussed Coulomb's law, but that's how we can actually quantify the lattice energy. Now, we're going to focus on lattice energy, but it's important to remember that our major focus is that the exothermic process is due to the reverse of lattice energy. So it takes energy to break a bond, but if we flip that, that's actually exothermic. So we're putting energy in to break the bond, but if we flip that reaction, we actually get energy back. So looking at Coulomb's law, remember K is the proportionality constant, Q1 and Q2 are charges, and D is the shortest distance between the centers of the cation and anion. So basically that means D is the distance between the nucleus of the cation and the nucleus of the anion. So the farther away your ions are, the lower the energy. The closer they are, the higher the energy. So lattice energy increases with increasing charge. Okay, so if we have +2 and -2, the energy will be higher than if it's +1 and -1. And it also increases as the size of your ions decreases. Okay, because that means they're going to be closer together. That bond is going to be stronger, so it's going to be harder to break. So remember, lattice energy is the energy required to break that bond within the ionic compound. And then we're going to focus on the opposite. Okay, so by accounting for all three of these energies, ionization, electron affinity, and lattice energy, we can actually get a very good idea of all of the energy that has to go into a process like forming sodium chloride. Okay, this also helps us explain the octet rule, and we focused on this when we looked at ionization energy, but for instance, sodium has a low first ionization energy and then a higher, significantly higher second, because once it loses that first valence electron, it is in the noble gas configuration. That minimizes energy and makes it much more stable. Okay, now we're going to focus on covalent bonding and some simple Lewis structures. So in a covalent bond, the electrons are shared. So ionic bonding was all about transferring from the metal to the non-metal. Now we're focusing on sharing the electrons. And there are several interactions within a covalent bond. So we actually have the attraction between the electrons and the nuclei, right? So that's an attraction. We also have the repulsion between the electrons, right? Your electrons are going to repel, but also your nuclei are going to repel. So for a bond to form, the attraction between the electron and the nuclei must be greater than the repulsion. If the repulsion is too great, then the bond isn't going to form. So sharing electrons to make covalent bonds can actually be demonstrated using Lewis structures and Lewis diagrams. And so we're going to focus on this much more, but we start by trying to give each atom the same number of electrons as the nearest noble gas. So we want each atom to have a full octet, 8 electrons. And so you have the example for hydrogen, which remember, hydrogen only needs 2 electrons. That's the duet rule. But notice chlorine has 8 valence. 1, 2, 3, 4, 5, 6, 7, 8, right? The line, single line represents 2 electrons. These 2 electrons go to both atoms. Okay, within Lewis structures, we have lone pairs. Okay, so lone pairs are the electrons located on only one of the atoms. And then we have bonding pairs, which are the shared electrons within the bond, right? So they can be represented by 2 dots or by 1 line. It's important to distinguish between these terms because we're going to focus on this once we get into formal charge and once we get into shapes. And then we have multiple bonds. So some atoms share only 1 pair of electrons. This is a single bond. If 2 pairs of electrons are needed, this is a double bond. And if 3 pairs of electrons are needed, this is going to be a triple bond. Okay, so what is important to remember is that single bonds are the weakest, triple bonds are the strongest. Okay, so again, single bonds are the weakest, triple bonds are the strongest. As well as single bonds are the longest, triple bonds are the shortest. So single is weakest and longest, triple is strongest and shortest. So that's very important to remember as we look at multiple bonds. So then if we want to distinguish if a compound is ionic or covalent, the simplest approach is to focus on the metal and nonmetal. Okay, metal and nonmetal is ionic, nonmetal and nonmetal is covalent. Okay, that's going to be your simplest approach. However, there are exceptions. We can get into looking at charges, and sometimes the higher the charge, it might not necessarily act like a metal, it might act more like a nonmetal, or we could have metalloids, right? Metalloids can act as either one. Sometimes your electronegativity difference might not be correct, and we'll talk about that in the next lecture. So what is the best thing to do is just to look at the properties of the compound, right? If you have the properties of the compound, specifically melting point, that's really going to help you distinguish if it's ionic or covalent. Very, very high melting points mean it's ionic. If it has a lower melting point, that means covalent bonding. So simplest approach is going to be metal, nonmetal is ionic. But if it's a metalloid or you have a, just something that might not seem right, look at the properties of the compound. So that is it for this video. If you have any questions, make sure you fill it out in the WISC form. Otherwise, we will continue on with looking at bond polarity and electronegativity in the next video.